So good morning to all those who joined afterwards. So we were trying to solve the Schrodinger equation for the hydrogen atom. And as I have mentioned before, it involved a lot of steps. So I'll just go through what we've already done before. So first, what we found was we looked for common eigen functions of L square and Lz, because we know that the eigenfunctions of the Hamiltonian for the hydrogen atom will also be eigenfunctions of L square and Lz, because they are it's a spherically symmetric potential. And this solution is also generally valid for any sort of central potential, but we'll talk about the hydrogen atom. Then once we found the common solutions, we found that they were Legendre polynomials. When we solved the equation for L square and Lz, when m, which is the quantum number for the L square operator, that was 0. Then for m not equal to 0, we found that the solutions can be derived from the Legendre polynomials, and these are called the associated Legendre polynomials. So there was a straight formula. Okay. Then in lecture 20, we wrote out the Hamiltonian for the hydrogen atom in spherical coordinates. That is what you see on the screen now. And we saw that it was a sum of a radial part and 1 by r square multiplied by an angular part, which was exactly similar to the Hamiltonian for or similar to the operator for L square. Then we used that knowledge to simplify the equation for the Schrodinger equation for the hydrogen atom, and we used the solutions for the angular part, which we call spherical harmonics, and then we obtained an equation only for the radial part. Okay, so this is the so what I've written as H electronic acting on psi, that was the part for the, that's just the radial part of the equation. Sorry, no, we have not done that before. So I wrote H electronic here as a radial part and the part which depends on L squared. Then we use the eigen functions of L squared, which are also common with the eigen functions of Lz, and we could remove the angular part entirely. And finally, we arrived at this equation. This is the radial equation. Now, to solve the radial equation, what we did was several variable changes. So, and our goal was to get it into some sort of known form so that we know the solutions. Okay? So, we didn't want to bother with actually solving the differential equation. We wanted to get it to some form whose solutions or set of solutions were already known. In trying to do so, we made a variable change where we defined a u, which was r into r. Then we saw that then we could separate out the Hamiltonian into an effective potential and sort of kinetic energy term. And then we said we will look for the bound solution. So from an analysis of the effective potential, we could see that we would obtain a set of bound solutions. And there may be also unbound solutions, but we're only looking for the bound ones, because the bound ones will be the confined, the quantized states. And we're only looking for the quantized bound states of the electron in the hydrogen atom. We spoke a little bit about the normalization, but that was pretty straightforward once the spherical harmonics are normalized. And then you could normalize the radial part separately as well. And then when we wanted to solve for the bound solutions, we made some more variable changes, which basically involved removing constants to simplify the form of the equation. So we defined a capital X from the small r, where r is equal to a0x by 2z, and this was and then x became a unit-free quantity, and we wrote our equation in terms of x, and we reduced the domain of our energy eigenvalues to the bound solutions by writing it as minus k square. Now we'll proceed from here today. So now our main goal is to obtain kappa, which is related to the energies eigenvalues of the system. It is lecture 21. Okay. So our goal today is to solve okay. So kappa square is equal to minus E0 by 2z square. Okay. Now we'll do something that we've done before. We'll try to guess the form of U. First in the limiting cases, and then we'll generalize it to an ansatz, and then try to see what solutions we end up with. So the first limit is when x tends to infinity. So the limiting solutions. So basically x tends to infinity means r tends to infinity also. And then the equation becomes d squared u dx squared equal to kappa squared u. Okay. Now this is a standard equation form. We've encountered this many times. So this implies that u is equal to there are two solutions to u, which are of the form e to the power plus minus kappa x. Okay. And the general solution will then be u is equal to some constant in e to the power plus kappa x. Let's put the minus one first, and then b is equal to e to the power plus. This is the general solution. But remember, in quantum mechanics, we only want to normalize it. Did you ask something?
Ma'am, have we taken kappa as positive here?
Well, yeah, I guess that is sort of implicit here. Yes. But if it's negative, you have to take the other one.
Okay.
Basically, you have to select one, and then normally you take kappa is positive implicitly. That's true. This is the general solution, and then since we want it to be normalizable, like I was saying, you say that this is not a valid solution. You only take the capital B equal to 0 part of it. Okay. We want solution to be normalizable. It's a similar argument from before. So this is one limit. Then the other limit, before we go to the other limit, okay, so now we have some kappa x quantity in the exponential. And we'll change our variables again. So again, changing variables, we write rho as kappa x, okay, which is equal to kappa z by 0. Okay. So this is another change of variable. And we look at the equation again. So then it becomes minus d squared d rho squared plus L into L plus 1 by IISER by rho u into IISER. Now the goal of doing this variable change is to isolate the kappa as far as possible. So we don't want kappa to disappear because that is related to my energy, but we don't want it to be in every term because that will complicate our sort of form of the equation. And mostly you will see in standard forms of differential equations the sort of constant term that you're interested in that is isolated in one term, either on the right hand side or somewhere. So here it's not on the right hand side, but it's still in one term if I change make this variable change. If I don't, then kappa is so if I stick to this one, then I have a kappa square here, okay. And then this will, so if I bring it to the left and try to solve it, I will basically end up with a little more complicated thing. Okay, I mean it's still in one term, but it's not. It's like a kappa square, and it doesn't help me get to a standard form. So again, this is a wise after the event. So all these change of variables are like that. People have done it and tried it and found that these variable changes simplify my solution. So that is why you follow it. Okay, it's not like you can guess it all the time. But here the idea was to remove the kappa as far as possible and isolate it into some sort of simple term where there is only kappa. Okay. And then once I've changed the variables, I can again look at the one of the limiting solutions, that is rho tending to infinity, which is basically the same as x tending to infinity. And then I get u is equal to e to the power plus minus rho. I mean, that is straightforward. But now let's look at the other limiting solution, which is 2, which is rho tending to 0. When I look at rho tending to 0, then my equation becomes then I can make a guess. So now I'll make a very general guess because here I have.
Can you scroll up a bit?
Yeah.
Okay, thank you.
So here I guess that u is equal to some general form rho to the power p. And then when I substitute, I get p into p minus 1 rho to the power p minus 2 is equal to L into L plus 1 rho to the power p minus 2. So you see why I guessed it to be a power solution, because I could see that I would get the same power of u once I did a double derivative and once I just divided by rho squared. So then I would be able to just cancel it and get a solution. P into P minus
Ma'am,
1.
what is P here?
P is just, I'm guessing the form of U as rho to the power P. P is an
Oh,
integer.
okay, ma'am.
Yeah. So P into P minus 1 is equal to L into L plus 1. And the solution that I get is P is equal to minus L, or P is equal to L plus 1. Okay. Therefore, my, again, general solution is some constant rho to the power minus L plus some other constant rho to the power L plus 1. Now here, if rho this is rho tends to 0 limit, remember, so 1 by rho to the power L diverges if rho tends to 0. So this will diverge for rho tends to 0. So we remove that, and we say that our only normalizable limiting solution, so our normalizable limiting solution is if rho is equal to some constant into rho to the power L plus 1. Now, so we've got two limits, rho tending to 0 and rho tending to infinity. So now we go to the ansatz.
And so that e to the power minus rho will, you're saying that will just become 1, so we are not considering that one. That's what you're saying.
E to the power minus rho, that was the limit for rho tending to infinity.
Okay.
So that is one limiting solution. So when rho tends to infinity, my differential equation gives this solution, e to the power minus rho. Okay, here also I'm actually choosing e to the power minus rho. And here, in the limit rho tending to 0, my differential equation gives the solution, some constant into rho to the power L plus 1. So then I'm making a guess for my ansatz, which is for the general solution for all rho. Ansatz for all rho is U rho equal to rho to the power L plus 1 and some general function of rho, because now I don't know exactly what it will be, and the e to the power minus rho. So remember we did this for the, so which one did we do this for? For the harmonic oscillator, I guess, yeah? So you so you sort of assume a form where your limiting solutions are present, and then you multiply it with something general, so that you solve for that and then you obtain the exact solution. And the idea is that once you have the limiting solutions in place, the equation for W or the general part becomes simpler. I could have just said that U is a general function of rho and tried to solve the differential equation. But in that case, we are still solving the original one, and that does not look like any general form, so we don't know the solution. We're just trying to get to some form where we know the solution. Hello? Okay, okay. না না আমার আরো লাগবে, আমার আরো 15 মিনিট মতো লাগবে। আচ্ছা ঠিক আছে, ঠিক আছে। ওকে 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 ওকে। হ্যাঁ, অরিজিনাল লিঙ্কটাই সেম। ওকে। Okay, so this is the thing. So I have my ansatz now. And now when I put it back into the differential equation, what I get is rho d squared W d rho square plus 2 L plus 1 minus rho dW d rho. So So I'm not showing you all the steps here, but this is just a substitution. You should be able to.
And for rho tends to 0, I mean, I did not understand how we could dissolve the 1 by rho term. I mean, that one is vanishing because both of them are tending to, I mean, large values, right? As rho tends to 0.
As rho tends to 0, the 1 by rho tends to infinity.
Right.
But rho to the power L will tend to 0. 0 to the power L.
No, ma'am. I'm saying that in the first step for the rho tends to 0 part.
Yeah.
Yeah, here, I mean, there was a 1 by rho term also, right, in the original equation. So I do not quite understand how that was, I mean, resolved essentially.
That one, yeah.
Since that is also big, right? I mean, that's not.
So that is. So that is actually. So if I change rho, and then I have a plus 1. I get your point. Okay. So actually this has also disappeared and this has disappeared. Both have disappeared.
The
So I'm
right
looking
hand
to
term is
my,
okay since that does not have 1
yeah,
by
that doesn't have,
anything.
yeah. But I
That is okay.
no, but that I removed entirely also. And it's not there anymore. It's probably so if you take the right hand side term to the left, and then you probably expand it in a series and the force something. I think I can't remember exactly what you do here. Can you just drop me a message so that I remember and I'll send you an explanation? But I can't remember
Okay.
at the moment. Yeah.
Ma'am?
Yeah.
Ma'am, in which equation are we exactly substituting the value of u?
Here, oh, this is in the original one before anything
Oh, okay,
else.
ma'am.
This is right at the beginning. So in the first one. No, sorry. After we substitute the word. So in this one. So this is the full equation.
Okay, ma'am.
Yeah. Okay. So once you substitute this ansatz, you get this equation in W. Okay. And then again for W, we take a general solution, which is a power series solution. And you obtain a recursion relation, just like before. So this is a K, okay? This is not a kappa. Don't get confused. So these are the Ks, and then this is a kappa. Wait, this doesn't look very good. And this is the kappa. Okay. This is what you get. Now again, we have to see what happens to this series. So here, the good part is that you have a one-step recursion because k plus 1 is related to k. So we don't have the problem of splitting things up into odd and even. And you only need one starting variable. So if you know A0, you can find out all other A's. Okay. So that is the good part of this recursion. And now let's look at what happens if this series does not truncate. So if it doesn't truncate, that is k tends to infinity, then ak plus 1 by ak is equal to 2 by k. Now, the form 2 by k does not directly give me a functional, so this recursion doesn't correspond to some function of k. I mean, I cannot write ak as a function of k if ak plus 1 by ak is equal to 2 by k. But if I write it as 2 by k plus 1, I know a functional form. And here I'm just trying to analyze if the series diverges or not. Okay. So it's not a problem if I take the functional form for 2 by k plus 1, because anyhow 2 by infinity and 2 by infinity plus 1 will not show much difference in behavior. So if this is the case,
Excuse me, ma'am.
yeah.
Ma'am, that last step, what is tending to infinity? Is it kappa or k?
It's k.
Okay, ma'am.
Now this
And
will
in that
confuse
whole
people.
equation, in that whole equation, we have only k, right?
Yeah, here we only have k, yes.
Okay, ma'am.
Okay, and then if ak plus 1 by ak is equal to 2 by k plus 1, then I can write ak as 2 to the power k by k factorial a0. Okay, and from this,
So, ma'am, are we substituting kappa by k plus 1?
no, this is also k.
Oh, okay.
This is also
Maybe you should use I or J,
yeah.
something like that.
I mean, the standard is to use k, so I wrote k, but it's a bit confusing. There's only one kappa, and it's. Okay, I'll do something. I'll just put it in a different color, and then you will not get confused. And everything else is k. So ak then can be written in this functional form, and then the series ak rho to the power k, that can be approximated as now this is the full series. Okay, so when so it will be dominated by the large terms. So as k tends to infinity, if you do have an infinite series, it will be dominated by the large terms, and this will be then equal to e to the power 2 rho. Okay, and this is certainly a divergent function. This is a divergent function. Thus, for normalizable solutions, again, we need the series to truncate. So the mathematical arguments by which we conclude that the series must truncate. That differs in the various problems that we've done. But this is more or less a general phenomena in quantum mechanics, all the problems, that if you take a power series solution, typically you should get truncating series in your solution. Otherwise, it will not lead to physical solutions. Okay. So, I can also reframe this by saying that we want a polynomial for W which is of a finite degree, capital N, let's say. Okay. Then, after a point, an plus 1 will become 0, and everything else on after that, an plus 2 equal to 0, etc. And this will give me a truncated solution. And that condition is, of course, that this factor 2 into k plus L plus 1 is equal to 1 by kappa. The condition is then that 1 by kappa is equal to 2 into n plus L plus 1. So kappa has now become is now related to an integer. Therefore, kappa has got quantized.
Ma'am, will it be plus 1 or minus 1?
Plus. So from k equal to capital N onwards, you will get 0.
K equal to capital L.
No, N.
Yeah.
Yeah. Okay. So, and here these are all integers. So n is equal to 0, 1, 2, etc. And small l also was 0, 1, 2, etc. Okay. Now, see, so for every value of kappa now, we can have many possibilities. So as long as n plus L plus 1 is the same, I will have many states with the same kappa. So then we're ending up with a very large degree of degeneracy for various combinations of n and L. And we can write this now as another integer if you like. N plus L plus 1 is also an integer, which we write as small n. Okay, and this small n is basically the principal quantum number which we have learnt about before, even from Bohr's theory. And that is the number which is directly related to the energy which is present inside kappa. Okay. So small n decides the energy.
Ma'am, could you please scroll up a little bit? Okay, ma'am. Thank you.
So we
In terms of
can,
fundamental constants, I mean, can you just, because we made many conversions, so what is kappa in terms of the fundamental units, like the
yeah,
A naught and
I'll write. So the energy expression was minus 2 z square e square by A0 kappa squared. So this is from where we introduced kappa squared in the differential equation. And now that we know the allowed values of kappa, I can write kappa now as then, oh sorry, I shouldn't have written. Okay, so kappa is then equal to 1 by 2n. So kappa square is 1 by 4n square. Which means that my quantized energy levels are minus. Okay, actually I should have written this over here. So this was my expression, and the quantized energy levels are minus 2n by 4n square. Minus 1 by n square. So these are the energy levels that you get even from force theory, and it depends entirely on n. Sorry. Now,
But N and L are not independent in this case, right? I mean, capital N and small l are independent, but not small n and L, right?
any two from, so since n plus n plus L equals to n, and this is the relation, any two are independent, and it is up to us to choose what we want as a quantum.
Okay.
Yeah, we'll talk about that a little bit more. Let's see. So for each n then, for each n plus L is equal to n minus 1. Okay. So L must lie between 0 and n minus 1, right? Because capital N starts from 0. And then capital N also must lie between 0 and n minus 1. We will have multiple states with different L and capital N values which correspond to the same energy. So we can try to count them also. So C N, and remember that when we solve the radial part, we solve it for a given value of L, because the Hamiltonian contains an L. N, L, and L. So when N is equal to 1, then L and M have to be both 0. And okay, and remember M and M, so this is a separate one. This we know from before, that M goes from minus L to plus L. So this we know from before, right? Okay, so N, L, and M. Then for n equal to 2, I have two options. L can be 0, L can be 1, and M can be 0 when L is equal to 1, and it is equal to plus minus 1. And when it's equal to 3, then we have 0, 1, 2. Here again 0, and then 0 plus minus. Okay. L is equal to 1. Oh, here also I will have a 0. L is equal to 0 and If it is 3, then 0, 1, 2, 0 plus minus 1. And here you have 0 plus minus 1 plus minus 2. So then the number of states, and they are degenerate because they have the same small n value. So for this one you have 1, n equal to 1. Then for n equal to 2, then I have 1, 2, 3 and 4. So there's 1 from here and 3 from here. They're of the same energy, so that's 4. Then from this one I have 1, 3, 5. And together I have 9. And I can generalize this now for n, that it will be n squared. So the number of states of for a given principal quantum number n with the same energy is n squared. Got it? So now we've spoken a little bit about the eigenvalues. And one more thing now that is also very interesting and is very special for the hydrogen atom. That is what happens for the energy between different values of L. So you see that I have solved my radial equation for a given value of L. But my energy ended up depending only on small n, which means that in an accidental way, my solution or the energy eigenvalue from my radial part is turning out to be equal for different values of L. Now that is pretty strange. I mean, there was no need for that to happen. Okay, but it does. So this is called an accidental degeneracy in the hydrogen atom. So how to think of it? So let's see. So if I want to draw the energy levels of hydrogen, I have, so I'll just write the 1 by n squared because that is what it depends on. So this is 1 by n squared plot. No, all the energies are negative, so I should draw it in this way. So this is minus 1, which is the lowest energy state. Then I have n equal to 2, so that is minus 1 by 4. Then I have minus 1 by 9, and then they get closer together. Okay.
Ma'am, should we not write minus 1 by n square?
Yeah, okay. That's right. So this is basically related to the energy. So the energy levels get closer and closer together as you go up in energy. This is the ground state. These are the energy levels for L equal to 0, let's say. And then I have L equal to 1, and what I find is that my spectrum shifts by 1, but it is still exactly parallel with the L equal to 0 states. And then for L equal to 2 again, you start higher, but you still have the same energy level. So this was not guaranteed, but it so happened that that the form of the equation gives you this. So this is called accidental degeneracy. In the hydrogen atom. It's not a true degeneracy. Our equations told us that that you will have 12 plus 1 values for a given small n. And it also told us that m will range from minus L to plus L. So those were guaranteed mathematically. But the fact that the energy will only depend on n, and for various L's, in spite of solving them separately, you would get the same energy. This was not guaranteed. Get my point? So this is an interesting thing. In fact, something, if you do another problem which gives you a similar, which is quite close to a hydrogen atom, let's say something like a spherical infinite well. So a sphere inside which the potential is 0 and outside which it is infinity. So a particle confined to a sphere. There also you will not see this degeneracy. There you will have a shifted spectrum, which is perfectly natural. But in a hydrogen atom, somehow you get this accidental degeneracy. And this was not resolved for a long time, and the resolution is actually quite complicated, so I will not go into it now. I will just give you the Eigen Functions as well, but I will not speak too much about it. Oh no, okay, before that I should say why I chose L as the quantum number. So someone told me that capital N could also be a quantum number that I choose. So why not? It's basically just that capital N is not a very physically motivated quantum number. Capital N is the degree of the polynomial W. So that is not a physical quantity. Small l, on the other hand, is related to the angular momentum. So it helps us visualize things better. So that is why you choose small l rather than capital N. Okay. So the quantum numbers that you choose N is pretty obvious since it is directly related to energy. Out of N or L, you choose L because it is related to angular momentum of the electron. And M is related to Lz, and anyhow M is pretty distinct from the rest, so you don't have much choice. So you choose M. So these are the three main quantum numbers that you get from this solution. If you include the spin quantum number, that is like an addition. So here we are solving the non-relativistic Schrodinger equation. So the spin quantum number does not arise directly from the equation. Okay. But knowing that there is spin, you can assign a spin quantum. But if you solved the Dirac equation, let's say, instead of the Schrodinger equation, which is the relativistic version of the Schrodinger equation, then your spin quantum number S would also appear naturally, like M or L or N from some mathematical criteria. Okay. Now, what is the form of this wave function solution?
Also, ma'am, if we have assumed that the nucleus is stationary, right, in this solution, so
yeah, so
that can be moving, like.
We have assumed that the nucleus is stationary. But if you did assume that so if you consider the nuclear part of the wave function as well, it is also possible to reformulate the equation in terms of relative motion, and your solution will still follow this a similar path.
Okay. Because I was thinking that the potential part will then change drastically if nucleus is also moving.
No, not really. I mean, you will end up with the reduced mass instead of the mass of the electron at various points. Like in your equation, the small n that I have been writing, that will change to mu, the reduced mass of the electron and the nucleus. But the equation still takes a similar form.
Okay.
It can be solved in a similar way. So that is actually the beauty of central potentials. Like I was mentioning at some point that if you have a spherically symmetric potential, you can follow the same procedure as the hydrogen atom. In fact, if you have an interacting system where the interaction depends only on the separation, then also you can reduce it to a equation which looks like a central potential equation. So you can do the same thing. Okay, now the wave function. This is a bit complicated. I don't expect you to remember the forms. If something is required, then the form will be given. So this wave function, what did we take? We had taken the ansatz to be rho to the power n plus 1. Okay. And then there was a w. And we found that the w depends on the eigenvalue of the equation, of course. And since we are solving it for a given value of L, it also depends on L. Okay. And then we have the e to the power minus rho. Sorry, so this was the u bit. So this was the u bit that we did, but this is psi. So remember that u was equal to rho u was equal to r into psi. Right? So I have to divide by r. So this is divided by r. And then I have the angular part as well, which we had obtained before. So this is my psi. And now since I did a lot of variable changes, I have to go back to r if I want to write everything in terms of r. So this is equal to, and I can also introduce a constant for normalization purposes. So this is a, and then I have, so r is sort of like, it's some constant into rho, right? So I can, and I have introduced a normalization constant, so I can shift those constants into a and say that r is just like rho. And then I can write it as a rho to the power L, w n l rho. So that's a prime. Or I'll put a prime here and this can be a. Minus rho. This is now my equation, and if I shift now, so I have a ZR by A0 L. Okay. Then W of ZR by A0 e to the power minus ZR by NA0, I believe. I hope this is correct because I'm just copying it out. Haven't really worked it out yet. 1 minute. So NLM is approximately this.
Excuse me, ma'am. Am I audible?
Yeah, I can hear you.
Ma'am, from that first step to second step, are we taking the rho by R as 1? Is it like that or something else?
Yeah. So R is basically some constant into rho. So I'm just shifting the constant bit into capital A prime and converting into capital A because I want to cancel the rho in the numerator.
Okay, ma'am. Got it. Yeah. Thank you.
Yeah, so this is probably it. Okay. Now W is a polynomial of degree capital N, and this is the source of nodes in your wave function. So the first term is a continuous function. There are no nodes. This one. The exponential is also continuous, so no nodes. So the radial nodes will all come from W. The angular nodes will of course come from Y. Okay. So this is it. And what about the form of W? So I told you that we tried to get our equation in a form which is a standard form. But then I didn't end up telling you what the solution to the standard form was. So the standard form that we got with the W is this one. Okay. Now mathematically, the solutions to this equation are what are called Laguerre polynomials. So W is formed from Laguerre polynomials, and in particular these are the associated Laguerre polynomials. I will not go into the details of this. So I have done enough for the Legendre and the Harmonic polynomials, and this is even more complicated and clumsy. So I'll just give you the general form of the solution, but you don't need to remember it. Okay? So this is just so the Rodriguez formula again for Laguerre polynomials is, so there are two numbers that every associated Laguerre polynomial is associated concerned with. So that is capital N and L. As a function of x. So in our case, it would be the x would be rho, or it would be r, depending on which form you take. Minus L by N factorial. is the general form of the associated Laguerre polynomial. And in terms of the Laguerre polynomial, the radial function or the solution is, what did we write? Some constant into e to the power minus zr by na0. So that's my rho. Then I have z by na0 whole to the power l, and then multiplied with the Laguerre polynomial for n minus l minus 1. So that's basically capital N, and then 2l plus 1 of 2z by na0r. And C has the value. This is coming from the normalization of R, capital R. Z minus 1 by 2 and then plus L factorial. Okay, so this is very clumsy, you can see. But the good thing is that this was already done once you got to the same form as Laguerre. You didn't have to find out the solution. But if you write it more explicitly, it looks a little bit nicer. So if I write
Ma'am, 2 by n e naught to the power of 3 by 2. Is it 3?
yeah, it's 3. It's 3. So let's write the simplest one, which is psi 100. That is 1 by root of pi a cube e to the power minus r a0 for z equal to 1. This is the ground state of the hydrogen atom, the lowest energy wave function. This looks pretty simple, and this you will probably remember as well. And if you want a few more,